Hey guys, Mr. Hallman here. We're moving right along through factoring and we're actually moving on to our next lesson. So after spending 2 weeks talking about reverse FOIL, today what we're going to talk about is factoring completely. So the good news is we're not going to be learning anything that's brand new. Instead, what we're going to be doing is we're going to take what we have been doing the past couple weeks and we're going to put it all together into a cohesive process. So let's start with just a redefinition or recalling what factoring means. Remember, when we say that we're going to factor, that means we're going to break something down and write it as a product. So here in example 1, if you want to take a second, I will tell you this is a GCF problem. So you're going to have to factor using the GCF. So go ahead, if you want to pause and try this right now as a little warm up to get us thinking about what's going on here, go ahead and do that. Okay, let's take a look at what we have. So I know this is a GCF for a couple reasons. One, when I look at the coefficients, they're all even, so I know that they all are multiples of 2, so I could factor out a 2 at least. I also see that each one has an x and a y. So when I factor out the GCF, I'm going to be factoring out the numerical GCF as well as the variable. So let's start with the numbers. 12, 6, and 4. The largest or greatest common factor between all of those is indeed 2. So I'm going to factor that out. Then we look at the variables. I have x cubed, x to the fourth, x squared. If you recall from GCF, we factor out the smallest exponent, which is the x squared. Then I look at the y's. I have y squared, y to the third, and y. The smallest exponent there is y to the first. So I'm only going to factor that out. That's my GCF that goes out in front. Left over goes inside the parentheses. So what do I get when I factor those things out? Well, if I had 12 and I factored out 2, or basically divided by 2, that's going to leave me with 6. And then the x cubed, I took 2 of the x's away, so I still have 1x. And I had 2 y's, but I took 1 of those away, so I'm still going to have a y. So when I factor out the GCF, my first term becomes 6xy. Let's go to the middle term. Minus 6 divided by 2 is 3. We had x to the fourth, but we took 2 of those out, so that becomes x squared. And we have y to the third, but we took 1 of those out, so that becomes y squared. And then we look at the last term. We have the plus 4x squared y, so 4 divided by 2 becomes a 2. And I factored out both of the x's and the y. There is no variable term left over. So this would be our final answer. 2x squared y times the quantity 6xy minus 3x squared y squared plus 2. Today what we're going to do is we're going to be using that method of GCF as well as our others, dealing with difference of squares, perfect square trinomials, and reverse FOIL. And we're going to look at how do we factor completely. So let's move on to our next example. Okay, so let's look at what it means to factor completely. First, you can see up here our definition. When we say that we're going to factor completely, that means that we're going to break down each part until it cannot be broken down any further. To be honest, in previous lessons and examples, we haven't had to worry about that issue. But today what we're going to do is we're going to look at what happens if I do factor something and then I can still break what's left down in some other way. So the example we're going to use to start with is example 2 here. You can see 27n squared minus 3. Now you might look at that and think, because you see the n squared and you see only 2 terms, you think about maybe this is a difference of squares. Unfortunately, it's not, because 27 and 3 are not perfect squares. So instead, if I'm thinking about what other methods of factoring could I use, the only one that I can use right away is a GCF. So I'm going to factor out a GCF of those 2 things. Think for a second, what do you think is the GCF? If you said 3, you're correct. We can't factor out a variable because the second term doesn't have an n, and the GCF between 27 and 3 would be 3. So now I have my leftover expression. If I factor the 3 out of 27, that becomes 9n squared. And if I factor the 3 out of 3, I can't just leave it blank. I have to have something else. Well, that leaves me with 9n squared minus 1, because that's why we multiply the 3 by to get back to 3. But now if I look at this expression here does look like maybe I can do something to it, because it's 9n squared, which actually, if I think about it, is a perfect square because it's 3n times 3n. And the 1 is 1 times 1, and I'm subtracting them. Guess what? This is a difference of squares. So what we're going to do is we're going to break that down further. We're now going to take this, and the 9n squared minus 1 becomes 3n plus 1 times 3n minus 1. But here's the thing. We also had factored out the 3 as part of the GCF. That has to stay out in front. Now at this point, when I look at my terms, can't do anything with this 3. I can't do anything with this 3n plus 1 to factor anything out, nor can I factor anything out of the 3n minus 1. This gets me to my final answer. And that gets us to our process here for factoring completely, because I don't want to have to guess and check every time. What am I supposed to be doing? What should I be looking for? So there's really 3 steps that we're going to use when it comes to factoring completely. The first thing we're going to do is we're going to check, is there a GCF? If there's a GCF, I want to factor that out. If I hadn't factored out the GCF here in number 2 first, I may not have known that I had a difference of squares, because these are not perfect squares. So without factoring out that 3 first, I don't know that I can use another method. Then once we factor out GCF, the second thing we want to look for, are there any perfect squares? So that means that I'm going to be looking to see if I can use one of 2 methods. Because if it's 2 terms, remember 2 terms means that we're going to use a difference of squares, where we're going to split it up into different binomials, same terms but different signs. If there's 3 terms, then it becomes a perfect square trinomial, which is where we have the same exact binomial twice. And if neither of those work, the only other option that we have is reverse FOIL. And that's always going to be our last choice and last thing we look at. So GCF, perfect squares, reverse FOIL. Let's look at another example. Alright, let's look at our next example. Example 3, we have negative 10x squared plus 40x plus 210. So again, let's go through that process. First thing we're going to look at is, do we have a GCF? So the first thing I notice is each of these numbers ends in a 0. So yeah, it appears that we do have a GCF, and it would be 10. But in this case, notice that we also have a negative out in front here. So we're actually going to factor out the entire negative 10. Now we have to put the leftovers in. So in parentheses, leftovers, if I factor out negative 10, that would give me x squared. And then instead of plus 40 divided by negative 10 would be minus 4x. And then instead of plus 210, 210 divided by negative 10 is minus 21. Next thing we look at after we factor out the GCF is, do we have anything with perfect squares? So I'm going to check and see, do these have perfect squares? In this case, 21, not a perfect square. So I move on directly to my third and final step, which is, can I use reverse FOIL? And in most cases, because we're saying that we want to factor completely, yes, there's always going to be an extra step here. So we're going to go one step further. We're going to break this into 2 binomials. Again, I'm going to keep the negative 10 out in front. And I'm going to look at x squared minus 4x minus 21. So thinking about what we've done the past couple weeks. X squared breaks into x and x. I want to force my signs to work out to give me a negative here. Well, the only way to get the negative is to have 1 plus and 1 minus. And then I want to force my last multiplication to give me 21. So if I'm thinking about what my factors of 21 are, I have 1 and 21, or I have 3 and 7. And the key here is that when I do my check and I add them together, I should get -4. Well, that means I definitely want to go with the 3 and the 7. I'm going to go with the +3 minus 7, because now when I do my check, if we do the outside plus the inside, that's going to give us -7x plus 3x. That gives us -4x. So that would be it. And this is our final answer. -10 times x plus 3 times x minus 7. Let's look at another example. Alright, so in example 4, we have 81x to the 4th minus 16. Again, factoring completely, we try and follow those steps of looking for a GCF, then looking for perfect squares, and then looking to see if we can reverse FOIL. The thing is, we're not always going to use each of those factoring methods, and we might not always do them in the exact order that we think we might. If I look at this case, 81 and 16 do not share any common factors. And while the first term has x to the 4th, the second term doesn't have any x's. So in this case, there is no GCF. However, I do know that 81x to the 4th is a perfect square. That would be 9x squared times 9x squared. I also know that 16 is a perfect square. That would be 4 times 4. So we're actually going to use our difference of squares in this case. So we're going to set it up, split it up into the two binomials. So we would have 9x squared as the first term in each one. And then we'd have a +4 and we would have a -4. Now at this point, since I'm factoring completely, I should be able to do something else. And again, what you might notice is that in both of these, I have 9x squared and 4, which means that I have perfect squares again. The problem is 9x squared plus 4 can't do anything with that. That stops the way it is. There's no way to factor when it's a sum of two perfect squares. But in the other set of parentheses, we have 9x squared minus 4. This is yet again another difference of squares, because 9x squared can become 3x and 3x. 4 can become 2 and 2. So that means I can once again break that down into two binomials. I can break it into 3x plus 2 and 3x minus 2. Meanwhile, we still have this quantity here, the 9x squared plus 4. So I have to also bring down that set of terms. So now what I end up with is a final answer where I actually have three sets of parentheses. I have three quantities: 9x squared plus 4, 3x plus 2, 3x minus 2. That becomes our final answer. We can't factor the 9x squared plus 4, and we can't factor the 3x plus 2 or 3x minus 2. So in this case, we factored completely, but we only used one method twice. We didn't use a GCF or reverse FOIL. So that's one thing we want to be aware of. We might not always have a GCF when we factor completely. Let's look at our final example. Alright, let's take a look at our final example here. We have 4x cubed minus 2x squared minus 6x. If you want to try this one on your own, go ahead, feel free to pause, and then check in with your answer afterwards. Otherwise, let's walk through our steps again. There's 3 steps to factoring completely. First step is to look for a GCF. Again, I notice that between 4, 2, and 6, those are all even. So yes, there is a GCF. I can factor a 2 out of all those. So we'll bring the 2 out. But I also notice when I look at these 3 terms, I have x cubed, x squared, and x. They all have the same variable. That means we can factor out, in this case, the smallest exponent on that variable, which is just x. So now we have to have our leftover expressions. So if I divide everything that's there by 2x, that's going to leave me with 2x squared minus x minus 3. At this point, I see 3 terms, and I know for a fact that this and this are not perfect squares. So I'm going to have to use reverse FOIL to help me here And this is where we're going to need to do the reverse FOIL that we talked about last week. Because 2x squared, when I split that up, I want to force it to work out. I have to split that into 2x and x. I also know that I need to use different signs because the last term's negative. The only way to do that is to get a positive and a negative. So I'm just going to plug them in and we'll worry about whether or not it's going to work. And then the last thing I know is that I want to force my last multiplication here to give me negative 3. Well, luckily, there's only 2 factors for 3, and that would be 3 and 1. So let's take a look. Now that I've split that up, I need to do my check. And remember, the check is the outside plus the inside, and it should give me the middle term, the negative x. So in this case, outside is negative 2x. The inside multiplication is positive 3x. But then when I add those together, that gives me a positive x. That's a problem because I wanted to end up with negative x. So, simple fix. We're going to take the signs and we're going to switch them here. Instead of having the plus and then the minus, we're going to put the minus first and then the plus. So now when I do my check, the outside here would be positive 2x. The inside would be negative 3x. They add up to negative 1x. That's what we want. That means this is our final answer. 2x times 2x minus 3 times x plus 1. I can't break those binomials down any further. When we talked about reverse FOIL, we should always end up with expressions like this where we have an x term and then a constant term. This is factoring completely. You really want to make sure that you try and follow that checklist. GCF, perfect squares, reverse FOIL. Otherwise, if you have questions this week, don't be afraid to send me a message. Reach out to me via email. We'll have our Zoom meeting on Wednesday. I'd be happy to talk with you then and go over some of these things together. Also, as we're winding down, again, I would encourage you to keep up with your work. And anything you need help with, please let me know. Hope you guys are all doing well. I miss you. Be good to each other and take care.